All right, everybody, welcome back to another session. Thanks for being here today. As we talked about in our last class on Monday, we were looking at machine learning applications for univariate ARIMA models. ARIMA, again, stands for autoregressive integrated moving average models. So autoregressive is telling us that this model is capable of calculating regressions and then calculating next or future time points based off of its own metrics. So it is a self-integrated model. The I stands for integrated, and then MA is the moving average. So again, calculating over time how the average fluctuates or is altered. Today, we're going to move beyond these statistical models and kind of basic machine learning models. And we're going to move into machine learning for multivariate time series forecasting. Now, the major change here is in how we are going to set up our model. So previously, we were still working on stats models. Uh-oh, hopefully I didn't break this. Hold on one second, guys. It's trying to execute a giant amount of code. And okay, here we go. So just wanted to make sure we terminated that before we tried to keep going, so we weren't wasting memory. So the major difference between today's model and the last day or the previous day that we were working on is the fact that today we will be using a neural network to train, or we will be training a neural network to forecast rather than using a statistical model. So of course, neural networks and the math behind neural networks are still based off of statistics and mathematical models, as well as computational theory, but they are more complex in both their structure and their function. So I've, of course, given you some resources. So we have these 4 packages that we've been working with up until now, which is Pandas, Stats Models, Scikit, and TensorFlow. TensorFlow is the new one for today. TensorFlow is a package specifically for training neural networks. The goal of TensorFlow is to really make it easy for anyone to train a neural network. The problem with making it easy is then people don't always understand what is happening. So I'm going to do my very best today to explain every step that we take and why it is important. Another issue with TensorFlow is that it is very computationally intensive. So just like on Monday, how I was saying, we moved into this Colab environment, these Jupyter notebooks, because I'm worried about this computational intensity and how it will affect your machine. TensorFlow is known to be computationally expensive, and there are other packages that are trying to get around this. So one example is TinyGrad. TinyGrad is a software package written by Geo Hotz or George Hotz, who's not classically trained. He's your stereotypical hacker, and that's the world that he came up in. Now he owns, I can't remember the name of his company, Comma AI and TinyCorp. Comma AI designs a self-driving car module that can go into any car. So you can buy it for like Toyota Camrys or whatever other vehicle you want. But TinyGrad is his answer to a deep learning framework that is less computationally intensive. So you can see it's 1,000 lines of core code, whereas I think TensorFlow is maybe like 10,000 lines of code. So it is a significant decrease in the amount of computational power required to run this package. Now, again, we're in Colab, so that's not a huge issue, and we should be set to TPU, so we're using a tensor processing unit, which also should speed up our processing time. So we're kind of set up pretty well here. And the first thing we're going to be working on today is a univariate neural network pipeline. Before we get into our pipeline, let's go over some of the basics of neural networks. So in our file over there, you'll see a bunch of links to different websites. And these websites are here to, of course, help explain what we're going to be working on today. So this is what we will basically be building. And we'll start over here on the left. This is a diagram of what an entire layer or structure of a recurrent neural network would look like. So basically on the left here is the summation of it. So you can see the green is the input. So you basically provide a neural network with some data. It then goes through a processing block, which is the neural network itself. That neural network typically has a feedback loop to process or feed some of activation or loss or weights back into the unit. and feed that forward into the next time step. And then based off of this, each of the time steps can spit out an output, which then can be aggregated into a total value to help optimize the model. So basically with recurrent neural networks, you have time step by time step starting at time 0, and it repeats this structure or this architecture over and over again until you reach the final time step of the problem that you're trying to solve or of the neural network. But this is only one type of neural network. There are actually two main kinds. So within machine learning, we talked about supervised versus unsupervised learning. Well, within each of those disciplines, you have, of course, different architectures that go with supervised or unsupervised learning. So two of the big ones right now are CNNs and RNNs. CNN stands for convolutional neural network. RNN stands for recurrent neural network. So the big difference here is the ability to process temporal data or information that comes in as sequences. So the RNN, the one that we will be building today, this guy right here, is the neural network architecture that is best laid out for dealing with temporal data. Okay, so I want to stop there and allow anyone to answer any kind of or to ask any kind of theoretical questions you may have, because I know that this is a way more intense or complex topic than what we've been dealing with. So does anyone have any questions, whether they be philosophical or about application when it comes to neural networks?
So I guess I have one question. Are we going to be comparing CNN and RNN?
Absolutely,
no?
yeah. So we're gonna do the RNN today, and then we'll do the CNN on Monday. We'll be analyzing handwriting, which is like the classic. So like this right here, for example, is what exactly we'll be doing on Monday in Monday's class. So basically, we'll be feeding in a set of pictures to a convolutional neural network. It'll break each of the pictures down of handwriting imagery into pixel values to record the gradient as well as the structure of the image. And then all of those will be fed in based on a structured or segmented photo pattern into the convolutional neural network. And so basically each of those inputs would be recognized as a segment of an image, which then gets fed into a dense layer, or excuse me, not a dense layer, a hidden layer, and then from that hidden layer to another, and then finally to your output. So that's the big difference here is convolutional neural networks are primarily used for computer vision, for object recognition and patterns and images and segmenting images also, whereas recurrent neural networks are used for primarily temporal or sequential data, so forecasting, for example. And there is the best of both worlds. There's a bunch of attempts to combine these two different models, but the most commonly used one right now are neural network transformers or deep learning transformers, whatever you want to call them. And if you are interested in these kind of different structures, I would recommend you read this paper called the Vanilla Transformer. And that is from Google's team, I believe. Let's see. We can go to Neptune AI's page. I think they have a link to it. No. Anyways, we probably won't get to transformer architecture. Transformers are far more complex. They require 3 to 4 different positional encodings, and also a lot more layers and more structure behind them. But to answer your question, Robert, in a long-winded way, yes, we will be doing both. The next one will be the convolutional neural networks for handwriting recognition. Okay, so any other questions? Okay, so we will keep going then. So recurrent neural networks, while this may be a complex topic or a complex concept, you use them every day. Autocorrect on your phone is based on a recurrent neural network. So it's recognizing you have a machine learning algorithm that has basically been trained on human language, similar to like ChatGPT or any of those other kind of inferential models. They're trained on the structure of words based on English or whatever language, and then they use the weights and losses to have feedback loops and to try to predict what word you were trying to type. So it can autocorrect to the word you wanted to type. Also, this is how predictive text works. So based on the sequence and the query of the words that you have written so far in that sentence, it is capable of predicting what the next word is. So you use this machine learning algorithm or architecture all the time. You just might not have known it. And if we dig in a little bit deeper today, what we're going to be working on specifically, and actually this is the one I wanted, what we'll be working on specifically is a long short-term memory. I'm not going to ask you to remember all the parts here. It's a lot of math. And honestly, the implementation of it is much simpler than the math. But basically what this diagram is showing us is that internal architecture of what we were just looking at. So each of these A blocks on the screen here represents one of these internal LSTM cells. So these LSTM cells basically take an input X, they get some feedback from the previous time point about input X at the previous time point. It takes that and weights it or provides it with a weight, sends it through, processes that information, gives you an output. And that's happening at multiple time points throughout that cell. And then that produces the average of those weights and values and the feedback information and passes it to another variable X and then lets that feed forward into the next cell. So this is how we can account for this temporal data in such a elegant but yet complex matter, because this is called long short-term memory. So it's basically a way of providing the machine with information about the X number of previous time points, and then the machine being allowed to use the weights and values from the previous time points to compute the future time points through one of these long short-term memory cells. And again, complex topic, much easier in its implementation than it is to explain mathematically. So that kind of catches us up on what we will be dealing with today. There will be some other things like atom optimizers and mean absolute errors that we'll talk about here in a little bit. Nothing too complex that you need to worry about right now. As always, I've provided you with the base of our project that we're building today. So this is from, let me see, Manish A. Jetva. That's how I'll say it at least. And he basically did exactly what we're going to try to do today. So time series forecasting with univariate and multivariate data sets. And he took a kind of unique approach to it, only in the sense that he was very serious about his plotting. So like, for instance, this right here is an example of some of the plots we'll be producing today. So he's got the weights and loss function on the y-axis and then the time steps on the x-axis. So he's predicting, or he's showing the historical values for what the model predicted, as well as the true future value. And then later on, he throws in the model's prediction based off of its current training state. So it's actually a really cool visual way of representing the weights and losses in your model, and also showing how close your true future value is in comparison to the model prediction. And then with that, we will also tack on an MAE, the mean absolute error, to compute the accuracy of our model. But we will get there when we get there. So to start, we're going to start with the univariate example, just like what we were working on last time, working on a univariate data set. So the first thing that we always have to do is install some packages if we need them. Since working from Colab, it's always just a good idea to make sure you have everything. So we're going to start by installing TensorFlow, Matplotlib, and NumPy and Pandas. We'll just hit the run over there. Should say we've already satisfied the requirements. And we'll keep going on. The next thing to do is import the packages that we're going to need. So from datetime, since we're using a temporal data set and we want to use the date as our indexing, we're going to use the datetime. From datetime, import the datetime subpackage, and then the time delta subpackage, which allows us to differentiate or create differencing between two datetime values. Then we're going to import NumPy as NP, Pandas as PD, Matplotlib, we're going to import PyPlot as plots, and then TensorFlow, the common TensorFlow abbreviation is TF. And that should be all we need for today. Next up, we're going to bring in our data set, just like we did in the last lab. And most of step one here is a repeat of what we did in the last lab. But just to make sure, let's take a look at our data set here. Our data set is in raw format as a CSV file. So we've got a bunch of different columns of information, and then everything is separated by commas. This is the same data set now that we've been working with for 3 weeks, so I'm fairly confident it's in a usable form, and we've cleaned it up enough to where we don't need to do too much of our checklist in our pre-processing. So we'll bring that in and save that as a new object called URL. And then from that URL, we're going to create a new object called data, which is just our data set. And data will be equal to PD for pandas.readCSV. We're going to pull in that URL, and then we're going to tell it how it's separated. And in our case, it's separated by a comma. And then let's just take a quick look at that data set. All right, so this is the initial data set that we get. Over on the far left-hand side here, you can see we do have a number or integer-based indexing system right now because data is being read as an individual column. In the date column, you can see that our data immediately is not sorted. This data set runs from 2008 to 2023. So we've got 2012 data showing up first. So however this data set was sorted as we stored it, it is not in a numerical or a date time format right now. And then of course, we've got a bunch of different columns that match different metrics that we're recording at this weather station. As I think I've mentioned previously, we have more information than we need right now. So in the next step, we're going to do some basic filtering and cleaning. So we're going to reiterate over that data object that we called earlier, and we're going to say data is equal to data, and then we're going to tell it what columns we want to keep from the data set. In this instance, I kept the date, the average temperature, average dew point, relative humidity, average wind speed, max gust of wind speed, total precipitation, total solar radiation, and the evapotranspiration. That's, again, more information than we need. We will not use all these features today. We'll only use 4 of them, but just keeping it there in case you want to do more with this data set on your own time. Because the things you will learn today, you could easily come back into this collab and keep adding on to the data set that we were working on. After we get the data subsetted in the way we want to do an operation on the date column because we want to index by the date. We want to incorporate that temporal aspect into the data set. So we're going to call in the data object, and we're going to subset the date. And we're going to say that the date column is equal to pandas.toDateTime, which is a function to convert those numbers to a date time format. And we're going to tell it that it's converting the data date column into date time format, and that the format that the column is in right now is year, month, day with slashes, not dashes, as you can see right here. Once we've got the date column properly formatted, we're going to take the date column and we're going to set it as the index. So we're going to say that the data object is equal to data.setIndex of date. So we're going to get rid of these integer indexing points over here on the far left, and we're going to take date and make it our index. And then once we've got that set as our index, we're going to sort the index, and then we'll view it just to make sure it did sort. Let's go ahead and run that. Looks like it ran. We originally had 2012 data numbers up at our top. Now we have 2008. You can also see that date has been moved down over here onto the side. So it's not being represented as a column anymore. It is being represented as our index at this point in time. It also has reduced the number of columns from, I think, 13 or 18, something of that amount, down to just the ones that we asked for right here in this first line. Another little hint to remember is you can take this and turn it into an interactive table if you'd like, and you can filter this table or sort it in whatever ways and formats that you would like. Again, this is another step that we did in our last group session or meeting together. We ran just our general checklist and quality assurance. So we ran data.isNull to check if there are any null data points, printed out how many null data points there are, and then described the data or got the info from the data about what format our data is in, how many rows we have, are there any null points, what are the names of the columns, those kind of things. We'll run that real quick. All right, so what we're seeing here is that we have no missing data after we've deleted off and only saved the rows that we want. Our date time indexing did work. We have 5,358 entries that run from 2008 to 2023. We have a total of 8 columns, and those 8 columns represent this information over here on the left. We can see that we have non-null counts right here. We have 5,358 non-null counts in all of our columns, which is good news. It means our data set is consistent across the board. We can see all of our data is being read in as float 64 right now, which is what we want. So everything is in a format that is usable further downstream when we're trying to compute any of our values or metric. Okay, so we're set up there. The next thing we're going to do is subset the data. So again, like I told you, we've got way too much information in this data set. We could totally work with this entire data set. It would just take us a lot of time and computational power to get this done. So what we're going to do is split part of the data set off for the thing we want to predict. And then we're going to split the remaining data up into training and test splits based on the temporal location. So let's go ahead and do that. So the first thing we'll do is create a new object called df data frame. And that data frame object will be equal to the data object we created previously. And then the average Fahrenheit is specifically what we're going to try to predict today. So we're trying to predict temperature still, and that's just subsetting it. And then we're going to ask for a plot of that data. And then once we've got that taken care of, got our subsetting taken care of, what we're going to do is run the train and test split. So like we did in our last session, we made a mask, which is basically just a filter statement. And that mask is equal to the data frame.index. So the total length of this data frame. And we ask for that specific condition. Oops. There we go. When it's less than the data frame.index -1 minus the time delta of days is equal to 1607. So this time delta, again, is a differencing equation. So basically what we're saying is from data frame.index of the -1 position, so less than the end of it, subtract from there the time delta and subtract 1607 days. The reason we're doing 1607, again, is because we have 5,358 days in our data set. So subtracting 1607 saves 30% of our data for our testing data set. And that's what we set up here. So after we've got that mask layer set up, what we do is divide it into our train and our test split. So we create a new variable called df train, which represents the specific variable we are interested in, average Fahrenheit. And we set that equal to the df, and we call on this mask filter. And so what that says is I want the entirety of the df data set minus 1607 points. So this should provide us with 3,000, I don't remember how many, 3,800 and something points. And then we tell it to create a copy of that and save that to the new object df train. With the df test, we do the opposite. So we're asking for all but the mask. So we're asking for this squiggly line basically means the difference. So in this instance, we're asking just for the 1607 days. And I think in actuality, the computer returns 1608 because of this -1 right there. Not a big deal. It's like 0.5% when we're talking about 5,000 entries. And then we do the same thing here where we create a copy of it and then save that to our test. And then we're just going to plot them so that we can visually confirm that they are divided up the way that we want. So we'll run that real quick. Should just take a second. There we go. So what you're seeing here is the data on our y-axis is representative of the average temperature over time. On the x-axis, we have the date, which we're indexing based off of. And our data for this station starts at 2008 and runs all the way up to 2023, up until, I think, mid-February is what we pulled. So you can clearly see this trend up and down, which is why we were able to meet the stationarity requirement or assumption of the ARIMA model that we worked with last time, because we have a neutral slope or a zero slope across the entire data set here. And in this instance, what we're looking for is to confirm that our training data set and our testing data set split up as we expected. And I believe they do, because you can see that the training data set is shown in orange, and it represents about 70% of our data up until about 2019, maybe a little earlier. And then you see that we have our testing data set from 2019 forward. So we're providing it with 70% of the information to train on, and we're saving 30% to try to make predictions on. Now, one thing we did not have to do in our last session was normalize our data. So in our last session, because the ARIMA model only has the assumption that our data is stationary, it does not have any assumption about the mean or standard deviation of our data set, we did not need to normalize or standardize. With ARIMA models, you standardize or create differencing in your models based off of whether the model is stationary or not. So because our data was stationary, it was not necessary to standardize the data. It can still be good practice, but that's just a matter of choice from the modeler's perspective. In our instance now, because we're working on a neural network, we do have to standardize our data or normalize our data. Neural networks, we want to limit as much of the possible error that could occur. So for instance, if a neural network is reading a value of 80 in one instance and 20 degrees in another instance, that's a wide range, 60 points, that could be misconstrued and weighted incorrectly in the model. So normalizing our data creates a scale of, essentially 0 to 1 for the model to work off of, and to then standardize every data point in the data set to match that scale, so that a 0.1% or a 0.1 data point that is fed into the model is equivalent to a 0.1 data point that is fed out of the model, which then can be converted to a real world value. So by standardizing, we protect ourselves and prevent any confounding variables or confounding data points in our data set and in our modeling. So that's the step we have to do now. This is still part of our pre-processing. So what we're going to do is take the data frame values that we created up above right here, and we are going to convert those to type float, which they already should be type float. This is just a confirmation or to be certain that we are doing it correctly. And we're going to save that as unidata, as in univariate data. So that's the new object now. And then the next thing we have to do is take our df_train data set, and we're going to convert all the values in there to integer. The reason for this is because the splicing function or slicing function that we want to use here will not subset an index that is in type float. So the df_train data set has to be in integer format. And I learned that the hard way setting this up. And once we convert it to the int, what we're saying on the inside here is that the length of the df_train data set is what we want to convert to the integer structure, or the integer type, excuse me, and all that should be changed or reset and resaved to the df_train object. So all this is saying is go over the entire length of the df_train object, convert every number or value in there to an integer, and then resave that as the df_train object. And the reason for that is because when we normalize our values here on these next two lines, we create two new objects, one called unitrain mean, unitrain STD, which is standard deviation. And the mean here is going to be equal to the unidata that we created up above. And within the unidata and the values of the unidata, we are going to subset or splice the df_train, and then we're going to calculate a mean for that entire data set. So we're saying from the beginning through the entire length of the df_train object, calculate a mean. And then we say down here for the standard deviation, the exact same thing. So we say within the unidata object, please take and calculate a standard deviation for the entire length of the df_train data set. So from the beginning through the end of df_train. And then we take these two objects that we just created and reiterate over the unidata object. And we say unidata, that object from up above, is now equal to unidata, the data points or these values that we had, minus the unitrain mean, and then divided by the unitrain standard deviation. All we're computing here, or all we're doing here, is creating a method for standardizing our data. Nothing complex, very simple math and arithmetic. We're going to run that. Shouldn't see any output. If we wanted to look at it though, we could go and say unidata and call it once we're done. Oops. Uh-oh. I broke it by writing a line of code. It just ran. Uh-oh. Let's see. Let's see. Okay, so I don't know why this broke. Maybe I need to rerun this. Okay, I don't know why that broke it. All I did was write uni_data to view it, and it did not like that. So we just won't view it. You guys
I
will
think
have
it's
to.
because you already ran it before.
Oh,
Because
okay, so I just
it ran for me.
okay, gotcha. And so yeah, it's nothing special. I was just going to show you guys that it does spit out values. So all you're doing is calculating basically a way to standardize your data. That's the easy way to explain it. So that's finally the end of step one here. Okay, so we just actually the easier way to view this is with our table of contents. So we just finished the data pre-processing and cleaning. All of that was a necessary step to be able to feed into our neural network. So now we're at step two of our pipeline, which is choosing our model. So our goal in this session is to use a neural network for forecasting future weather predictions. Now, the issue with this is that, as we talked about a second ago, there are a bunch of different types of neural networks and many different architectures that you could try. So we could try to convert, like for instance, we just calculated weights basically, or standardized values. We could take those standardized values and turn them into a heat map of an image where every pixel represents a different number in our data set, and then take those pixels and those images and feed them through a convolution neural network. But that doesn't necessarily make sense unless you have a temporal aspect that you're including in there somehow. So my point with saying that is that you can use a bunch of different types of neural networks to do the same thing. It all comes down to the user, the modeler, and the use case that you're using at the time. So for our first attempt, as I told you guys at the beginning, we're going to be using a recurrent neural network, and we are going to specifically use the long short-term memory cell to calculate our recurrent neural network here. And the reason for this is because this architecture is specialized for temporal data, and we are going to try to simplify this to an extent by running the univariate use case, which is what we've been preparing our data for up until now, the first time around on the current neural network. And then in the future pipeline, what we'll do is we'll transition into the multivariate data set. So just to give you guys a better idea of what we're looking at here, I drew out some basic diagrams of what our architecture looks like right now. Come on, slide over. There we go. So these are essentially the pipelines that we're getting ready to build, with the exception of the softmax. So the algorithm that we're using there isn't 100% certain, but we'll get to that here in a second. So what we started with was a stored data set. And in this step with the stored data, we did a bunch of pre-processing and converted our raw data into a standardized or normalized data set in the normalized function. From that normalized data, what we can do is feed that normalized data into that recurrent neural network architecture, where it's going to go time step by time step and calculate the weights and the losses at each time step, and then feed some of that information forward to calculate the next time step. Based on how that model or how those weights are distributed and how the activation functions work in the recurrent neural network layer, all of that data gets fed into a dense layer, which is basically it'd be like the equivalent of a hidden layer that then aggregates all the information. So it takes all of the inputs from the recurrent neural network time point and feeds them all into a smaller high density layer that can compare all of the data points from all of the inputs at one time. From that dense layer, what you do is feed it into what's called a softmax, or some other kind of averaging algorithm. The softmax is basically a collection point. So it's the funnel point where all of the data from the raw data set has finally been funneled down and processed and comes to a final collection point before output data is spit out. So this is essentially a way of like calculating the probabilities or the weights or possibilities that a action or event will occur based off of what the neural network model is telling you. And then once it's calculated those weights, you can transform those weights and those probabilities into possible output data. So this is scenario one that we're going to build right now. In scenario two, we're going to do the exact same thing, except because we're adding multiple variables, we're going to increase the complexity and add a second recurrent neural network into the mix. So once it's processed in recurrent neural network 1, the weights and action functions, or excuse me, activation functions, and basically the output of neural network layer 1 are fed into a second recurrent neural network to compare the different probabilities between the two neural networks. And then after the second layer of the recurrent neural network, the second layer of the LSTM, it's fed through a dense layer, then the softmax, then the output. So all we did to increase the complexity in a multivariate situation was add another layer of, essentially at this point in time, because we're not going to get into the crazy details of these networks, this is basically just a layer of abstraction. It would be the equivalent of a hidden layer up here, because you don't need to know what's coming in or what's going out. It's just another processing layer that still contains that temporal structure. So we're, with this second setup, basically we're saying, okay, I've got a ton of variables right now, and all of them are dependent on time. So because time is such an important aspect, let's go ahead and add in another layer that can account for time. Once the second layer has accounted for time, then those weights, values, and activation functions and probabilities can be led through the dense layer to aggregate it all. And then finally through the softmax, and then give us output data. There is another option with this where we basically could have the neural networks running simultaneously here. So side by side, and then both of these neural networks can run through the dense layer. We probably don't need to worry about this too much right now. Either way should give you way more information than we get from a standard statistical model. And that's the interesting thing to us, right? We're just practicing right now. We're playing around with the numbers and trying to understand these architectures. So that's what we're getting ready to build. So this is pipeline 1 at the top for the univariate situation. This is pipeline 2 at the bottom for the multivariate situation. And so let's hop back over here, and we're going to start building the basis for our pipeline. So the tutorial we're following today uses kind of a unique structure. Rather than playing with the scikit-learn packages or anything, the person decided to define a bunch of their functions. And all these functions are basically doing is specifying the variables needed to calculate and to run the neural network further down the line. So like this one at the top here is defining the univariate data. So you provide it with inputs, which are data set, start index, position, end index position, the history size, so how much data to view, and the target size, so the position of where you want to view your data. And then it takes the input data, the data set that you give it, it tears it all down, and then it restores it as a NumPy array called data and labels. And that's basically what you need to know here. Another function that he created was the create time steps. So we indexed by date in his data set. The guy that we're following, he did not index by date. So this is just a way of making sure you're returning, or excuse me, you're getting a list of all of your time steps for the data set to be processed in the neural network. So it doesn't have to remember 2008. It can remember time step 1, time step 2, time step 3, and iterate through the data set. If you remember, our data set already has a row like that. But instead of going through and making sure that, or excuse me, not a row, our data set already has a column called date.1 or date period 1 that has the numbers in there that are supposed to be in sequential order. Instead of checking to make sure that they were, I just went ahead and used this function because it was already there. Then the last one that we need right now is a function to show the plot of the trained data versus the predicted data. So if you remember those graphs I was showing you where he had like the history of the data points and the loss functions, and then the X marked the spot for the true outcome, and then he had the circle dot for the predicted outcome from the model. That's this right here. So all he's doing is creating basically a wrapper to plot all of that in one step. So we can just write show plot and then the plot data, the delta or the time point he's viewing, and the title of the plot. So this is just to make our lives easier. And so we'll go ahead and run that. Should take no time. And then we're ready to actually start creating our univariate data. So we're going to use this function up here at the top that's going to divide all the data up for us. And we are going to build on that data. So the first two things we need to decide or tell the machine is the past history, which is the equivalent of the history size here. And then we also need to tell it its target size or its target location. So we're going to give that as two variables so that we can pass it to both of these two future lines, basically, or objects. And so here we're going to say that the univariate past history is 20, meaning that it can see 20 time points behind it. So in our model, the model is capable of seeing 20 time points into the past. The univariate future target is 0. So the reason for this, and I'll show you this time point down here, he's using 0 as the point of prediction. So because we're saying 20 time points in the past, that's how far back it can see, and it can see the history of the model and the function up to time 0. Time 0 he's using as a random point in the data set that he wants to make a prediction on. So time 0 is always his target value because he's leading up to that point, essentially. So I hope that makes sense. And then after that, what we're going to do is divide into our training sets and our validation data set. Validation data set, you could also change this to X test data, or it doesn't matter. It's a personal preference. Many people call them validation data sets, whatever works. So basically what this is going to do is take the uni data object that we created up above based off our DF train, and we're going to take that and split it into our training data set and our validation data set based off of the univariate data function. So in this first function right here, you can see that we're saying X train comma Y train will be equal to univariate data, the function we defined. Then we give it our data set, which is uni data. Then we're going to tell it its starting index, which is 0. And after its starting index, we tell it its ending index, which is df underscore train. So we're saying go from time 0 all the way to the end of df underscore train, which would be 3,000 and some odd time points. Then we're going to define the history size, which is the history size right here. And then the future target size, which is the future target of being 0, or at time 0 relative to the model, how does it respond? Then we do the same thing for the validation data set. So we have xval and yval, and we use the univariate data function to compute those objects. So we're going to give it our data set uni data. This time, because it's for our validation data, we want it to start at the end of the DF train data set. So DF train being the end, so 3,000 whatever data points, 3,750, it tells me right there. So that's the position where this one is starting. The end is none, so it technically is supposed to go to the end of the data set. You also could say df underscore test. Either way should function. These are both objects that the computer knows. So it knows that df test has a count of 1,608. In this instance, I'm just going to leave it as none. Shouldn't have any effect either way. Then we have our history again and our target size. So really the only thing that's different between our training objects up here and our validation objects down here is the starting and ending index position, which makes sense because we are working with a temporal data set. So at the top, we want to go from 0 to the end of the training data set. For our testing data set, we want to go from the end of the training data set to the entire end of the data set itself. So we'll run those, create those new objects, and then we're going to spit out some information about the history of the objects that we just computed. So all this is telling us right here is the past history for this data, the univariate data that we just created, because that's all we did. We computed some data. And it tells us that the target that the model should be trying to predict is 1.818. And if we plot that, we can see that that's what it's showing up here. This true future prediction is this 1.818. And it got that by calculating, placing the X train univariate output at time 0 and the Y train univariate output at time 0. And it shows us the history of all 20 time points up until that point in time. So what we can do with this is basically we've set up our background to be able to calculate and compute these values. Now what we're going to do is make a baseline calculation for this false or fake data set that we just made to make sure that the code is working properly. And so in order to do that, we're going to define a new function called baseline. Baseline is just equal to the history. The history is equal to this right here, all of this blue space that is shown on here as history. So we say, all we do is ask baseline to return np.mean of the history. So return the mean of all these data points, and then we can plot that on our data. So then we'll plot the baseline by using the show plot function, calling on x train at time 0, y train at time 0, and then the baseline function right here of x train at time 0. And then we give it the 0 and we tell it what its title is. Let's go ahead and run that. And there we go. So on a completely untrained model, we haven't even turned our model on yet. In a completely untrained situation, this is what the data shows us, what a simple model would predict. So starting 20 points back, we get the exact same history as what we had up above on this plot. And we have the same output prediction or true future instance, which is 1.818. And then the model predicts based off of the mean of the history here, right? That we have a model prediction of 0.75. So this is the true prediction shown as the X. And then the model prediction at this point in time is the green right here. So clearly this is not a good fitting model. And the reason for that is that this baseline model is just based on the history, the mean of the history of our data points, which we could calculate by hand. So that's without anything happening or without anything being done to the data. Now what we're going to do is instantiate the RNN, the recurrent neural network, and actually plot this data, run this data through our neural network and see what we can get. And when we're talking about neural networks, before we get too deep, there are two metrics or parameters we have to discuss. The first one being buffer size, the second one being batch size. So the buffer size is the number of elements from which the data is randomly shuffled before it's being passed to the next stage of the pipeline. So an example here would be the buffer of 100 means that TensorFlow shuffles the first 100 elements and then randomly selects one of them to pass through the pipeline. And the bigger the buffer you have, you can get better shuffling and better generalization out of your model. And then the second one is the batch size. So the batch size is the number of samples that are propagated through a network at a time. So if I have a batch size, for instance, here of 256, that means I'm taking 256 samples at a time and running them through the network. So a batch size of 32 means that 32 samples are being run through the network at one time. Now, larger batch sizes lead to faster training times, but because you're pushing so much data at once, you potentially could be overfitting the data, right? So your model may be making too strong of predictions or not accurately making predictions at that point in time. So we're going to go ahead and start the model here. Just remember to keep these things in mind. And we're going to set our batch size to 256. I feel fairly comfortable. Again, this is just our first pass at this data, but I feel fairly comfortable using a batch size of 256. That's just under a year worth of data. So if we remember what our data looks like, in theory, feeding it 256 data points at one time should help us either catch this downward slope or this upward slope, and in theory should predict the outcome to some degree of accuracy. It should be able to pick up on the slope and everything. So that was kind of the thought process behind that. The buffer size, we don't even have 10,000 elements. We have or on this univariate case, we don't have 10,000 elements. We have 5,358 elements. Buffer size, it just gives more space for things to get shuffled around. Not a bad idea to just leave it as that. We'll also use a buffer size of 10,000 for the multivariate situation. Then what we're going to do is create two objects called train univariate. First, train univariate is basically just telling it where our data is. So we call on TensorFlow and we say TensorFlow.data. And then we say, from this data set, I want you to take the tensor slices. And those tensor slices are equal to the X train uni and the Y train uni variables or objects that we created up above. Then what we're going to say is, for the train univariate situation, I want you to take train underscore univariate and I want you to cache it to the system. So everything else beyond this cache, we're saying, please save this to my current memory. From there, we're saying shuffle. So shuffle based on our buffer size. So take all of this information, X train and Y train, and shuffle it based off of our buffer size. And then we also tell it to create batches off of our based off our batch size, and then to repeat it for the entire sequence of X train and Y train. Once we've got that done, we do the same thing for the validation data set, except we're using xval and yval. And we also don't have to use buffer size here. We don't necessarily care to shuffle them, but we do want to batch them for the validation data set. So we'll run that. So all this is done at this point is created two new variables. So we've compartmentalized and shuffled and restructured and then saved these objects to our local memory. Now what we're going to do is actually build the LSTM structure, the long short-term memory structure. So first thing we always do is clear our session. There's always the potential you've ran another model and you could be iterating over the same model again. Don't want to do that. That's a very bad thing, and you can get lost really quickly. So we start with the clear statement. Then we're going to create a new object called the simple LSTM model, which is just a simple long short-term memory. And that will be equal to the TensorFlow.keras package. Keras is, you'll see that word a bunch more time. It's a specific sub package for LSTMs and other neural network architectures. Then we're going to call in the models and ask for the sequential model. Within the sequential model, we have a bunch of different parameters that we can feed into the network. The first of which is going to be layers. So the first layer that we're going to create, just as we saw here in our chart, is an RNN, a recurrent neural network. And in our case, we're specifically using the LSTM. So for the LSTM, we're going to specify the number of inputs and then the input shape that it'll be receiving. So it's going to take the X-train uni, and we're going to take that and go dot shape of -2 and then through the end. And then after the LSTM layer, we're going to add that dense layer that we have right here. And that dense layer, we're just going to say has a value of 1. That's the parameter. Okay. Once we've got the simple LSTM model defined, the next thing we do is compile it. And we're going to compile it based on an optimizer called Atom. And Atom, I believe I have this pulled up. There we go. Atom is a stochastic gradient descent model that's specifically designed for deep learning applications. So over here on the right, you can this is basically the of different inputs over time or over the number of iterations. So it's just a way of optimizing the model and computing the weights and losses in a way that heads towards the most optimal output over a shorter time period. And for our loss function here, we are using MAE, which is the mean absolute error. Again, like I said, I don't expect you to have this all memorized. I don't expect you to have this all memorized off the top of your head. But the MAE here is basically a summation of the actual output value minus the predicted output value. You sum all that up, and then you take it times 1 over the number of data points, and that is equal to the MAE. So similar to our mean error that we were computing the other day, where we want it to be closer, or our mean standard error, excuse me, that we were computing the other day. You want it to be closer to 0. That technically is a better fit. In this case, we also want it to be closer to 0. The nice thing about MAE is there's something called MAPE, which is mean absolute percentage error. So we'll actually compute the mean absolute percentage error for the multivariate case. So we'll go ahead and run that here. Takes no time, tells us how many parameters it has, how many trainable parameters it has. So it's showing that the LSTM is getting 320 parameters in. The dense layer is getting 9 parameters. So the majority of it is in this LSTM, and then the dense layer is dense as it sounds. So all the LSTM is feeding into that dense layer, which then can give us an output. So we've instantiated the model now. Now we're going to train and fit the model. When we're training and fitting the model, it's actually rather simple to set up here. We have to do 2 things. First thing we have to do is tell it how many time steps it's training on. That's this evaluation interval. So we're training it on 200 days at a time. And then the epochs is the total times to train it. So how many generations basically do we want it to be trained? So because we're just messing around, or we're not messing around, but we're learning this right now, I just did 20 generations. On an actual model, you may train it for 10,000 generations or 5,000 generations. It's just all personal preference or what the model needs. And you can always increase or decrease these numbers as you see fit. And then what we're going to do is create a new variable called history. History is just because that is all the points that have been fit to the model. So that's what the person called it. And history is going to be equal to simple LSTM model that we instantiated earlier. And then we're going to do the dot fit function that we've worked with previously. And we're going to tell it to train the univariate data set. Epochs is equal to epochs. Steps per epoch is equal to evaluation interval that we started up above. Validation data is equal to the univariate data we computed earlier. And the validation steps is equal to 50. All right, so we will run this one because it only takes a couple minutes to run, just so you can see how it runs. But we'll go ahead and move on to the next point down below, or the next part of our pipeline here. So this one doesn't take very long because it's a univariate situation. But as you get more complex with your data set, these things can take hours and days to run. So I do not recommend that you wait to the last minute to work with something like this. You need time in advance to be able to appropriately fit these models. Because remember, all we've done at this point in time is fit the model once. We don't even know if it was a good fit. What if it's a bad fit and you need to run hyperparameterization or hyperparameter optimization by doing that grid search that we were practicing in our last session. That grid search took me an hour for the second model, and that's on a TPU. If you were running that on your personal computer, you could be talking about 3.5 to 4 hours of training time. So some people, if they only have their personal computer available, they'll just set these up to run overnight and come back to it in the morning. So yeah, this one doesn't take very long. We're already on step 17. And you can see in the output here, it's giving us the time per step, the loss function for each of these epochs, and then the validation loss function. So obviously we want these numbers to be fairly close together. But once this finishes executing and saves, what we're going to do is make predictions based off of that data and then plot the data. So that'll be the next step here. We're going to say for X, comma, Y in val univariate, we want it to take 3 of the measurements at a time and run through this structure. So we're saying plot the show plot function where X at time 0 is a numpy array, Y at time 0 is a numpy array, and then comma, it's pulling the predictive values from the simple LSTM model, and we're running the predict function at X is equal to time 0, and then computing a graph that is just the simple LSTM model. So we'll go ahead and run that. It'll take a second because it is doing the predict function right here. And then this is what our current model is spitting out to us. So in its first iteration here, you can see we've got some wild numbers, but these are just random data points that have been chosen throughout the entire data set. And then it gets to time 0, it gives us the true prediction and then the model's prediction. So you can see we're still off by a bit. Then we have the next example, because remember, it's taking 3 of our examples and computing 3 of them. So for the second example here, you can see there's the model's prediction, here's the true value, and you can see the history is actually turning down, but the model was not able to accurately predict that because of the loss function here. So the loss function is too close together. It can't tell it's turning down. And then for the third time step, this is by far the closest one. We've got our history that's pretty wild. And then we've got our model prediction down here at the bottom and our true prediction up here at the top. So you can see it's this downward gradient that's getting the model prediction closest to the true prediction, but we still have some loss here. And the reason for that is probably partially it's because it's hard to predict a multivariate outcome based on a univariate input. It's going to take a lot of optimization. Eventually you could do it, but at this point in time, our model is just not that dense. Okay, now we're going to move on to the multivariate neural network pipeline. So basically we did the univariate pipeline to introduce all the concepts here. Now we're going to build on that and create some more complexity in our data set. So to do this, we have to start all the way back at the pre-processing stage because we've got to rebuild the data set to include extra features. So we're just going to create a new object called features considered, which is our total solar radiation variable, our ETO, which is our evapotranspiration value, and then our average relative humidity. The reason I chose these 3 metrics is 1, temperature is based off of how much sunlight is getting through the Earth's atmosphere, which would be the equivalent of our total solar radiation measured at the weather station. Our ET, evapotranspiration, is how much water is being evaporated from the weather station or from the atmosphere at the weather station based off of the radiation and the temperature there. So that's another way of measuring the loss of water concentration based off of the temperature or the intensity of the light. And then relative humidity. Humidity is how much water is in the air. If there's less water in the air, it's probably hotter. If there's more water in the air, maybe it's cooler. Also, this is partially guided off of our previous working with this data set where we saw that these variables were highly correlated, positively correlated, and highly negatively correlated to the average temperature measured at that time. What we do with this features considered object is take it and subset those out of our data set and create a new object called features. We create features and index them based off of our data index. So data is the overall data set that we created up above. Then we're going to call on the features head object just to show it, and then we'll plot these three features. So let's go ahead and run that. Takes almost no time. And this is kind of what we're seeing. So we have a pretty similar trend to what we had in our weather data, just peaks and valleys, peaks and valleys, peaks and valleys over time. But the thing here is we do see some consistency. So we can see that the ET and the total solar radiation, their peaks and valleys align, whereas with the relative humidity, it looks like the spikes in the relative humidity are at the low points in the ET and the solar radiation. So what I was saying, I assume may be correct, is as temperature increases, relative humidity decreases. As temperature decreases, relative humidity increases. And that's kind of what our data is showing here. So now what we have to do is take this data set and save that, standardize this data to our model. And this is the exact same setup that we did above. One thing I just realized that I did here that I don't like is I know we've used dataset before and I iterated over this dataset object. Not too happy with myself about that, but it shows that it's reading this data in, which is what we want, and we want to be able to compare it to the DF train. So as long as both of them are reading as the correct object. So I don't think it's a big deal, but this is why I get kind of, I guess not uppity, but this is why I get concerned about how we name objects and our naming conventions and styles, is because I did this to myself. I didn't even know I did it, but I know I've used the word data set in this notebook before, so we should not have used it again this far down. All we're doing though in this step is standardizing our data. So exact same setup as above. We're taking the features and the values that we computed here, saving them as a new object called dataset. Then we're calculating the data mean for the entire length of the DF train dataset and calculating the mean, then doing the standard deviation. And then we're standardizing just by taking the dataset minus the data mean divided by the standard deviation. So we'll go ahead and compute that. We're good to go. Next thing we're going to do is our model selection. So we're going to be using a multivariate LSTM RNN to create a neural network capable of multiple time step predictions based off of the given data. So instead of predicting only the one value that we were seeing here, this next neural network will be able to compute 20 values or 100 values into the future based off of the training data. So in order to do that, we do have to define a new function here, which is just called our multivariate data. And for the multivariate data, it's doing the same thing the univariate data did, except we have to specify these steps and if it is doing single step, which in our case is false. Okay, besides that, it's the exact same thing. It takes the data set that you give it, it divides it up, it saves them as NumPy arrays of data and labels. So we can run that and we're good to go. Next thing we're going to do is instantiate the RNN. Okay, so this is where it changes just slightly from what we did last time. You'll notice down here that the X train, Y train, X val, Y val to create our training and our validation data sets is the exact same. But what we had to change, or we didn't have to change it. What I chose to change here was the past history time. So in the past history, we did 256 days. To be honest, I don't remember off the top of my head. Let's see. Our evaluation interval was 200 days. So this time we went way up on the evaluation interval. This time we're doing 720 days, which would be almost 2 years. Our future target is 72 days. So we want to potentially predict 72 days in the future. Again, if we are giving it this long of a period, 720 data points, it should be on a upward or downward slope based off of our moving average that we've seen in our data set, right? There are tons of peaks and valleys here that it can predict off of. So hopefully by providing it 2 peaks and valleys, it can then predict off of those 2 peaks and valleys accurately. That's kind of the thought. And then the step value here is 6. The step is referring to the steps between the time interval. And that is defined up in this right here. We have step right there. So if single step, oh wait, no, excuse me, that's the wrong one. Step is right here. So it's saying range of I minus the history size, then find I and calculate the steps. So, and that returns the indices. So that is a necessity for the multivariate data function that we want to use to separate our training and validation data sets. And then we also have this df underscore val right here. Df underscore val is equal to the length of our data set minus the past history minus the future target. The reason we had to introduce that is because I was getting an error actually in the length of the validation data set while I was running this. So it was telling me that the length and size of our training data set and our validation data set were different. By introducing this as a generic iteration variable or iterable variable, it can continuously calculate the total length needed for the validation data set and then compute that when it runs the multivariate data. And then within the same block, I also put the multi-step plotting structure in here. So again, this is just another thing that the guy that we're basing our project off of or building our project off of used so that he could plot multiple data points at once without having to write all the code. So just to simplify our life a little bit. That ran no time. Now what we're going to do is start adding some layers for the complexity of this data set. So again, the first thing we do, as we did in the univariate situation, is split up our data. So we take the TensorFlow package and take from our tensor slices, and we slice up the X train, the Y train, the X val, and the Y val. After we do that for the train data, what we're going to do is cache that data, shuffle it, batch it, and then repeat that until we get to the end of the data set. For the validation data, we're going to take the valuation data and just batch it into certain sets and repeat that till we get through the data set so that we can compare to. And then what we're going to do is initiate or initialize a multi-step model. That's just the name of it. And the multi-step model is going to be equal to our TensorFlow Keras package, and the models we're going to call or instantiate a sequential model. And that sequential model, we're going to add layers to step by step. So the first layer is going to be an LSTM layer with 32 inputs. This 32 is not a number I chose. That's what the other gentleman was using that we're building our package off of. You can technically have whatever number here as long as you have enough inputs to deal with it. So this number could be 700, it could be 1,000. Just remember that the higher the input number, the more complexity you add. So that's what that is. That's the number of inputs it should expect. Return sequences, true. Yes, we do want our sequences to come out of there so that we can actually use them for further downstream processes. Then we tell it what the input shape of its data is. And once we finish that first layer of the LSTM, we add a second layer right here that is also an LSTM. In this case, we do not want it to return the sequences because it's being the sequences from the first layer of LSTM is being fed into the second layer of the LSTM. And this LSTM is getting 16 outputs rather than 32. And it's using an activation function called ReLU, which is related to the long short-term memory function that we're using here. So this is just a specific activation function with a different set of mathematical models that go with it. After that layer of the LSTM, we add the dense layer. The dense layer is expecting 72 inputs from both of the other two previous layers. And then we compile the model based off of the RMS optimizer or RMS proportion optimizer, which the RMS proportion optimizer does similar things to Atom, except we can add this clip value. So if any of our outputs lead to a value that is greater than 1, the model basically cuts it off. So we have a minimum value of 0, and we have a maximum output value of 1. After that point, it will not calculate anything higher than that, or it'll just chop it off there. And then our loss function here for our compile layer is the MAE, the mean absolute error. Okay, so we'll run that real quick. Okay, so now that we have our neural network instantiated, we've got our model built and compiled, the next thing we have to do is train the model. And this step takes some time. So in this instance, it took 16 minutes to run. That's not too bad, but I'm not gonna bother running it again just to make sure that we don't take too much longer. So in this case, what we're doing is building a new object called multi-step history. The reason for that is because we want to record history at multiple time steps throughout the entire model. And this multi-step history object is equal to the multi-step model. And then we call on the .fit function. And then for the .fit function, we have to tell it what data set it's working with. So our training data for the multivariate situation, we tell it how many epochs to train for, which is equal to the epochs that we specified up above in pipeline step 3. Then we tell it how many steps it has per epoch. Again, that's equal to the evaluation interval that we provided up above. And then we tell it what validation, where its validation data is, which is the val data that we separated up above, and how many validation steps to take. When we run that, it runs through all 20 of these epochs with 200 time steps each. And you can see the loss metrics and the validation losses over here. And what we'll do next is actually plot this data. So we'll define a new function called plot the training history, which basically just takes the range of the losses and the validation losses and then computes a figure for them. And then we can actually use that function to plot the multi-step history that we defined right here and see how the model performed over time. What we can see is that starting at time 0, we have a clear drop off in training loss. So after about, it looks like maybe 1.5 or 2 epochs, we get fairly level training loss, and we're still seeing a slight downgrade, but not really. It seems like the model kind of stagnated. Whereas with our validation loss, again, we see a clear drop off at about time 1, maybe 1.5. Then we have some gain in loss, then more loss, and then it kind of just iterates over itself over and over again. But you can clearly see a separation between our training loss and our validation loss. So we do still have some training that can be done so that this validation loss is equal to the training loss. So we still want to reduce this loss as much as possible. But for now, we'll keep working with this model. We're not going to worry about hyperparameterizing it today. We'll fine tune it in the future if we would like to. So what we're going to do with this data now is actually make predictions on this fitted model. So we're going to come down here in step 5 of our pipeline and say for x comma y in val data of the multivariate situation. I want you to take 3 of these time measurements at random, and I want you to compute a multi-step plot, which we set up earlier at x is equal to 0 and y is equal to 0. And then I want you to predict x at time 0 based on the model. So we'll run this. And we'll see some things that actually don't look too great, to be honest with you. We'll see that the predicted variables are very clearly clustering here. So we've got some differences in our data. In actuality, what I'm going to do, I don't like the way that this looks. I'm going to delete that right here, and I'm going to go rerun this. I'm going to retrain the model. So I'm going to stop right here. And Juan, sorry, I didn't know you were hanging on. Juan, I will be back. There you go. It's okay. And so what I'm going to do right here, I'm going to stop right here and I'm going to retrain this model. So I'll be back in about 20 minutes. All right, everybody, we'll get back at it. That time, I spent the time training again because what I realized while I was waiting is we re-instantiated the model. We restarted the model, but when we restart the model, if it hasn't been trained, that's why our data may have been looking funky as we saw down here when we were making predictions. So I retrained the model. That time it took 17 minutes, 26 seconds, 17 and a half minutes. Now we'll rerun this, defining the functions to validate loss over time. There we go. We can see it's almost exactly the same as what I had before. Let's see if it runs these predictions any better, if the model looks any better. That looks way better. This is what we should have been expecting. So let me go ahead and explain to you what we're seeing here. So on the y-axis, we are seeing the measurement at each time based on the standardized value. And then we are seeing on the x-axis up to 120 time steps back in time, which is based off of our parameters that we fed to the model. And then we can see that each of our models is running all the way up to time 0, which is where we ask this model to make predictions. So in the last model where we had reinstantiated the recurrent neural network, but we had not fit the model again, we were just kind of getting a clump of data points for our predicted future. And that was because it didn't know what the history was, because the model had not been fit and it didn't have anything to compare to. So now that we've trained the model, we can see very clearly that based off of the trained model, when we get to the end of our history at time 0, when we look at the true future predictions have a little bit of a spread to them, which is not surprising. The data points aren't exactly equivalent to our predicted future. And then the predicted future values are almost directly in line with the shape of our historical curve, and they also match the peaks and values that we would expect from our historical curve. When we look at the second example, we see the exact same things. Our predicted future pretty closely aligns to our true future. We do have some data points that are off, which is not surprising, as we have not adjusted our hyperparameters to match this exact model. And the third situation, we see the same thing. So it looks like this model fit is actually pretty decent. Just based off of our visual, or looking at it visually. What we need to do now is actually throw a number to it. So as you saw when we were instantiating our models, we compiled the model and used the MAE loss function, which is the mean absolute error. So we can actually calculate the mean absolute error for our model to compare our predictions to our true values, so that we can actually determine mathematically how well this model fits the data and if we need to make any more adjustments. So the first thing we're going to do is basically create the test data set. So we are going to go in there and create a new variable called test data multi, which will be equal to our slice tensors for the validation data set, so the X val and the Y val. And then we're going to batch that based on the batch size from the model up above. And then we're going to define the number of steps in the test data. So steps is going to be equal to the length of the test data multi. Again, this step is just to ensure that the output array is the exact same length as the test data array, so that they match up and our functions will run. Then we're going to create a new iteration variable called MAE values. This is the mean absolute error value. So basically, we're going to create this so that we can store our mean absolute value values from all of our data points in this one list, and then we can compute an overall mean absolute error. So after we've created our iteration variable, we're then going to create a for loop that's going to say for X and Y in the test data multi. And then we're going to divide them up by X validation and Y validation. And then we're going to make predictions of Y based off of the X validator using our multi-step model that we just fit up above. And then once we have our predicted values for Y, we're going to create a new object called MAE for mean absolute error. And that'll be equal to the TensorFlow Keras package and then the metric subpackage. And we're going to look up the mean absolute error, which is built into there. And for the mean absolute error, we're going to give it the Y val and the Y predicted values based off of X. So the Y validation is what we actually have from up above. The predicted are based off of our model. And then we're going to turn that into a NumPy array. Once it has MAE calculated, we're going to take the MAE values object we created above and append each of the MAE values to that array from up above, or that list from up above. Once we're done with that for loop, we are going to calculate an overall MAE by taking and creating that new object and making it equal to numpy.mean of the MAE values. And then we're going to print out the overall MAE for this model. So let's see how well this model actually fits our data. Pretty decent. So the overall MAE is 0.1366. So if we converted that to a percentage, this model is off. The predictions for this model are off by about 13.66%. So if we subtract it from 100, that would mean right now we're sitting at essentially and 86% and 86.3%. So 86.3% of our data after one round of training without optimizing or tuning our hyperparameters is fitting the data properly. So that's not too bad for one round. And if we wanted to continue to improve on this model, what we could do would be go into our model setup where we're training the model and change our parameters. So maybe we run our tuning grid search like we were doing in our last case, and we find out the past history should actually be 1,000, the future target should be 62, and there should be 47 time steps in each iteration. So that would be the next step, is fine tuning those parameters to get the MAE as low as possible and making sure that we can accurately predict future values. And another aspect of this may be that we also have more variables that we could add in. So previously we only included these three features: the solar radiation, the evapotranspiration, and the relative humidity. We also could add in some of the other things like the dew point or the leaf wetness, or we could add minimum and maximum temperature. We could add the wind speed. So we have a bunch of different other things. We could add total precipitation. Any of these things, including them in the model, would only potentially improve the efficiency of the model. What we have to be careful of is that we don't overtrain the neural network, which will lead to overfitting of our data. Because right now we're really not that far off. After one round, we got 86% of the data fit into the model. So we just need to fine tune that, figure out where we can make some small improvements, and try to go for somewhere between 90 to 95% of our data being fit by the model. And making sure with that, we still are not overfitting the data. So that's what I had for you guys today. I hope you guys enjoyed this session. I know that we're moving into more complex topics. As we move into these more complex topics, I will do my best to continue to explain them. If you have any questions about this that you did not ask during this session, please feel free to contact me over Discord or over email, whatever way you would like. Your homework will be out tomorrow. But for now, I hope you guys have a great day and an even better rest of your week, and I'll see you next time.